Hi, welcome back and welcome to the channel if you're new. If you've tried learning Houdini, you probably have heard of RBD, and most likely you've tried to get a little bit of an introduction into RBD. So this here is a video that I wish I had when I started my Houdini journey into RBD. And actually in this whole video, we'll cover an entire fundamental introduction to RBD and actually how to use it. It's going to be very beginner friendly. I'm only going to assume you know a little bit of introduction into maybe navigating Houdini, but if you are brand new to Houdini, please check out the rest of the channel. There's lots of introduction videos to help get you started and then hopefully give you enough information to follow along here. Download the files, have some fun, mess around with this, and then if you're interested in learning more, this is the first of 5 RBD sections inside a premium course I offer and have actually been teaching for quite a while. But this is Level Up Houdini, so kind of my more intentional learning path if you are really looking to get some more Houdini practice. So you can check that out here if you're interested. But this RBD section is going to be extended and have tons of additional information there. So definitely check that out if you want to learn more. Ask questions in the comments and then subscribe to the channel if you want to learn more Houdini. So awesome. I really do hope you enjoyed the video. A lot of work has gone into this and I hope you have some good luck on your Houdini journey, learn some cool stuff, and maybe make some cool ideas. And if you do, share them below. I'd love to see what you create. But good luck with the lesson, and I'll see you in just 1 second once we get started. So awesome. I'll see you soon. Welcome back, and welcome to Level 6 Simulation Fundamentals RBD Introduction. This series of videos you're currently watching now is Section 1 of the RBD Introduction level. We're going to break down RBD into these 5 general sections just so we can have a nice and consistent approach to learning these core fundamentals. So the first of these sections is going to be covered in this video section you're watching now, and it's the RBD Introduction Fundamentals. So in this section, we're going to explore the core fundamentals of RBD. Specifically, we're actually going to use the SOP level RBD Bullet solver, but we'll get into that and quite a bit more in just a second. But we're going to learn how to control and set up different parts of a simulation. Section 2 is going to be the RBD Introduction Basic Constraints. So in this section, we're going to learn the core introduction to constraints, what they are, how to create them from scratch, a few different ways actually of how to create them, how to control them, and then how to actually use them effectively in a simulation. Section 3 is going to be RBD Introduction, RBD Examples. So in this section, we're going to take what we've learned so far and apply it to some basic examples to get more practice actually setting up our simulations. So those are going to be very helpful, and they're going to be really the application of Section 1 and Section 2. Section 4 is going to extend further on the foundation we've set so far, and this is going to introduce the idea of fracturing. So in this section, we'll explore multiple different ways of fracturing. So from simple to more advanced setups, we'll be able to control exactly how we want to fracture, and we might even introduce some ideas of why you would use one over the other. And then the final section is going to be RBD Applied. So in this section, we're going to practice a little bit more complex setups, which you might consider more practical to what you would be doing for your own shots and your own projects. So this is going to introduce some ideas of clustering, some more complex constraint setups, and then the multi-material destruction, which is going to be combining maybe concrete, wood, glass, and metal, and maybe even a few other materials as well. And then the way we're setting these up is going to be determined a little bit by fracturing and then a little bit by constraints. And then ultimately, once we choose to render our simulations in later levels and put all this knowledge into practice for our simulation boss battles, which are going to be a lot of fun. We're going to get practice applying these all, and it's going to be definitely really exciting. So make sure you download the files for section 1. For section 2, 3, 4, and 5, those files will be in the different sections for those specific videos. Currently, these other ones are empty, but inside section 1, we do have all of our prepared examples ready to go through. So awesome. That's going to be all for the introduction for how this level or how this section of the level is going to be structured. In the next video, we're going to jump into section 1 and introduce a little bit about what we're going to cover, and then cover some basic theory that's going to set us up as we keep learning. So awesome. I'm going to end the video here, and I'll be back in just 1 second. Welcome back, and welcome to section 1 of RBD Introduction Fundamentals. We're going to dive inside this geometry container here and introduce a little bit about how this section is going to be covered or structured, excuse me, and then learn a few of our general introductions for the information that we're going to need to actually start applying this solver. So this is the SOP level RBD Bullet solver, and the reason we're going to use the SOP level solver rather than creating our own .NET is it is a lot easier to set up, a lot more artist friendly, and we can do many things in this solver here. And once we cover most of the stuff we can do here, we might expand into the DOP level solver later, but this is a wrapper actually for the .NET solver. So we don't actually need to set up any of these ourselves. The SOP solver's been created, nicely organized, packaged, and prepared with a bunch of settings for us to use. So by the end of this level, we're going to really have a fundamental understanding not only of how to use this, but how to actually create effective scenes. So the general section for this video is going to be, firstly, section 1, we're going to learn the name attribute. We're going to learn about our packed geometry. We're going to cover the active attribute. We're going to cover the animated versus deforming attributes. And then we're going to do some fundamentals on the collision shapes. So the shapes of objects while they're being simulated, as well as controlling and modifying some collision object shapes, which are going to be really very, very helpful. So I'm going to rearrange a little bit here. And again, I would recommend downloading these files so you can follow along as well as modify and explore this file here. So we are going to be using this SOP level solver. I just mentioned that. And we can do many complex things. So the only reason, in my opinion, to expand into the .NET solver is if you want to learn kind of how it works under the hood, or if you have a reason for getting more control in your simulation that you aren't able to do with the SOP level solver. But we're going to be able to do some pretty complex stuff before we run into that situation. So the key principle is that the bullet solver, which is what this solver here is using internally, this RBD solver here, this requires packed geometry to work correctly. So packed geometry we'll learn about in this section here, and we have covered it a little bit before, but the way it's going to be working is this packed geometry is either going to be packed intentionally by us, or Houdini itself, and actually this little tool here will manage lots of the packing, unpacking, and transforming of our geometry if we choose to not do it ourselves. So knowing what's packed and what's not packed is going to be very important for debugging and actually working through our simulations, because if we don't do it ourselves intentionally, then Houdini might do it for us, but it might cause issues that we do not expect. So we should always be aware of what's packed and what is not packed. The general 4 attributes we'll learn about today, which I did set up a section for each of those. These are going to be the name attribute, which identifies unique objects within a simulation that is also used for constraints and simulating with low-res proxy geometry. So this is required. The active attribute is going to control if an object is active in a simulation. So whether or not it's being applied or it's being used in the simulation, an unactive object or an object without a active attribute set to 1 can still be used as a collision in our simulation. We're also going to cover the animated attribute, which controls whether an object's position and really its transform, so both its position and its rotation, is updated each frame in the simulation. This is not talking about actually simulating the object. This is rather having animated geometry being used in the simulation. So this is typically when you want to have objects involved in the simulation, so colliding, but not actually being simulated themselves. And then deforming is a little bit more of an extension for animated, so it controls whether the object's collision shape and its position. So and its transform, so its position, its rotation, and then the actual collision geometry is going to be updated each frame. So we will learn about this one, and there's ways we can use animated geometry, which we will actually in this later section, to kind of replace some of the use cases for deforming. But as we get into more complex setups, it's going to be helpful to have an understanding of both of those. So as we're using this bullet solver here, which is the RBD Bullet solver, Houdini, and actually this tool, which is an HDA created by Side Effects, will manage a lot of the packing, the attributes, the unpacking, the transforming, and a lot of the fundamentals for us, which is really helpful if we want to stay artist friendly. But we are going to learn about a lot of these attributes here, because if we are letting the solver or letting this tool do it for us, there's ways we can get confused, or we can accidentally have mistakes in the simulation that could have been avoided if we were intentional about how we're organizing our setups. So we're going to learn about all of these, and then we'll have the knowledge to debug when things go wrong. But we will all be trying to set up this intentionally. So everything we'll cover here is going to give you a full understanding of how to use this solver, and also how to prepare, debug, and work through lots of common issues you might have, and then also should give you enough of an understanding to start to expand your knowledge into more complex setups. So always, if something doesn't work, slowly try to debug, recap, make sure your attributes are working as expected, and then isolate individual and small parts of your simulation to slowly fix the exact error you're actually running into. So we'll get a lot of experience with those as we move through all of these. Part of these I will be doing a walkthrough, so like a node by node overview, and then for some of them as well, I will be kind of recreating these adjacent to here. So I might expand, modify, and kind of interact with these in a way that you can hopefully see exactly what's going on. But I would recommend maybe first watching this whole video or this whole section through once, and then definitely downloading these files, because playing with these and actually looking at our geometry spreadsheet, looking at these attributes and looking at exactly what's happening, and more importantly, actually just breaking things and fixing them, is going to be the most effective way to learn. So awesome. That's going to be all for section 0. That gives a good introduction to what we'll cover. In the next video, we're going to come back into section 1 and get started with what we need in order to actually make this work. So awesome. I'll see you in just 1 second. All right. Welcome back, and welcome to name attribute in Packed Geo. So in this example, I'm going to introduce you to this general network here, and we're going to start getting our hands dirty with the bullet solver and learning exactly what's going on. So actually, before I jump into this one, I think it might be more helpful for me to recreate this same thing down here. Now, I might not do that for every single one, but I really do want you to understand. So these videos might be a little bit longer than some of the other sections, but I think especially with RBD, you really want to know exactly what's going on, because then you can debug as you get into later setups. So I'm going to recreate this here. Very first thing I did is I used a box here, which is just our standard box. I'm transforming it up a little bit. So I get this transform node, hit enter, move it up. And then I've also got a grid here, and then I use my RBD bullet solver. So I have mentioned before, this is the SOP level solver, which we are going to use for a majority of our simulations. So what we've got here is we've got our geometry, we've got our constraint geometry in this second input. In our third one, we've got our proxy geo, which is the lower resolution geometry that we can use in the simulation. We will cover all of these later, actually, by the way. The collision geometry, which is in this case a grid, and our fifth one is a guide sim, which we might cover in later sections, but won't be covering yet. So that's the input to these networks, and it works in a similar way that a subnetwork, would work. So inside here, these multiple inputs are coming in, and we've also got, in this case, if I duplicate this output with 1, 0, and 1, I've got 2 outputs. And that's the same idea with our bullet solver. So we can have our geometry, and if we hover on this one, we can see at the very bottom of my network view, we see a name of what is actually being output from this dot. We've got our constraint geometry, which are going to be our simulated constraints, so the result of our simulation. We've got our proxy geometry, and then we've got this one over here, which are simulation points. So we'll cover all of these in a little bit, but really this is all we need in order to actually simulate. And I can click play, and it might work as expected because we've got this box, moved it up, and it is now being simulated. But the really important thing to note is that right now, as of this setup here, none of my input geometry is packed. And in this case, we can see because I've got 8 points here, 6 primitives, 24 vertices, and no packed geometry. If I had created a packed geo here or packed node here, we can see I now have packed geometry. But this SOP solver would actually create the, it would pack the geometry for us and simulate, and then it does a transform. So it takes the resultant simulation point and it transforms our input geometry back to that simulation point. So if I look up here, actually, which is the exact same setup, I can see my completed simulations on this left, which is the high-res geo, or this input here, being transformed to this point. So the reason we have a simulation point separate from our geometry here is that when we are simulating objects, we really only need to know the location of each individual piece, and we need to cache that. The reason we cache that is because caching a single point is a lot less expensive and takes up a lot less space than if we had cached the full geometry at each frame. So the way we work with that is we take a sim point and we transform our geometry, which we will cover in the next example. But we transform our geometry to the simulation points. That way we only have to cache our high-res geometry once, and we cache our sim points for every single frame. And then the other attribute we need to know is the name attribute. So if I look here at my incoming geometry, so select this node here, or even this one down here, there currently is no name attribute set. But if I look at my completed simulation, so the output of this bullet solver, we will now see a name attribute exists on the primitives of this geometry, and a matching one, in this case, actually does not exist on the proxy because there's no proxy geo connected here to the 0, 1, 2, so the third input of my actual solver. But in future cases, the name attribute is going to match so we can have high resolution geometry being transformed, or its position being copied to the exact location of a lower resolution proxy geometry. But we need to know that this name attribute is required, and this bullet solver in this case is creating it for us because we did not create it for ourselves. And on this sim point here right now, because this is just a single point, I can now look at the points on my geometry spreadsheet, and we'll see piece 0, which is actually the same name as my completed simulation, which is the first output here. And the reason that's important is because we will use this node, which I'll cover in the next example, but a transform pieces node to take the matching name attributes between my high-res geometry here, and it's going to find any points with the matching name attribute, and it's going to animate or transform that object to the points with that matching name. So that becomes very important for our simulations, for our constraints. We also will actually use the name attribute to define which object each constraint is really tied to and is used. And then also for proxy geo, which is going to be helpful for matching a very high resolution geo to lower resolution geometry that will be quicker to simulate. And then for this bullet solver, we'll get into these settings later, but everything actually is 100% default. Whoops, I'm going to ignore that error here. So I just created the RBD bullet solver here, geometry on the first one, or the objects I want to simulate on the first one, the grid, in this case on the 1, 2, 3, fourth one. And if I go back and I reset my simulation, we can now see it does simulate. So no settings were changed here. We can modify these, but we will only modify these as we need. So that is a very helpful reason that this is so nice, because right out of the box, this already works. So awesome. That is going to be all for this first example. In the next video, we're going to get started on example number 2. So I'll be right back, just so we have nice and tidy timestamps. All right, welcome to example 2 for our name attributes and packed geometry. This is a little bit more complex of a setup, but once we get some practice, it's all going to make sense. So I'll go a little bit slower than we might in later sections, but really understanding what's going on is going to be very helpful. So this is very similar. I've got a box. I transform it up. So if I hit space G, I can frame. On the left, I actually bevel it, which in this case, I don't actually need these nodes here to be actually enabled for my simulation to work. So maybe I'll show you what it looks like if I disabled these all. I've just got this now coming in to this side. I can actually cut this proxy geometry, and I've got my cube being simulated. So right now, currently as it is, this is the exact same setup as our first example here. But what I've done is, if I have a poly bevel here, I can create some different resolution geometry. And in this case, because my high resolution geometry is plugged in and there's no proxy geometry plugged into the third input, this bullet solver is going to use this high resolution geometry as the actual simulation geometry. So if I go here on the bullet solver to visualization, I can hit show collision shapes. And then I will see this little blue outline, which if I hit W for wireframe, you can see it a little bit better. But this outline is the shape of my actual collision geometry. So if I increase the radius of this bevel, we can see that the blue is a match. So it actually does match this same geometry. And if I simulate by clicking play, but I'm first going to disable this preview just because it'll simulate a little bit quicker. It is now simulated using this geometry here. And then the output of this right now is the high resolution geometry. Currently, there's no constraints. There's no proxy geometry because none of that is connected. And there's no simulation, or excuse me, there is a single simulation point. And then in this case, actually, we have another name attribute and we have a high resolution geometry here, which is being transformed if I use this transform pieces, but technically this should have the name attribute. So right now this is working as expected, but if there was any other object, then this single one, this transform pieces would not be working. So what we want to show in this case is this polybevel here is creating this high resolution geometry, and I also can have lower resolution geometry being simulated as the proxies. And what that means is instead of using this high res, so I'm going to take this polybevel, I'm going to make it 0.02, so make it a cube again. This is the transform. I'm going to make this a sphere now. So right now this is coming in as a sphere, and if I connect this to my third input, so right here, reconnect it to the third input, what's going to happen is if I show collision shapes, we can now see this sphere is the shape of my blue object. Or excuse me, the blue object, or the collision shapes, in this case, is the shape of my sphere, which is the shape of my collision, or excuse me, my proxy geometry here. And the reason this becomes really important is because once we get higher resolution simulations, we're going to want to be able to have low resolution geometry. So these proxies control the actual physics of our simulation and then copy those, the high resolution geo, in this case the cube, to those points after the simulation is done. So now if I enable this flag down here, because I have proxy geometry connected, we can now see, if I click play, I've got this sphere here. There will be no constraints, and we can see actually that this sphere is what's being simulated because it is rolling. There's a single simulation point here. And now if I transform pieces, this cube is being copied to the sphere's sim points. So we are transforming this with the transform pieces, and I can even delete this and re-add it back. So transform pieces. Geometry to transform is on the left. So this is the high resolution geometry, and template points I put on the right. And right now it is matching by name, but because there is no name right now on this input, there is a name on the point here for simulation points, but this is just matching the only piece to the only sim point. The better and the correct way to actually work with this one would be to have a name attribute here on the primitives. So I create my box, which is a name attribute, and I create the same name attribute on my proxy geometry. And now here, at the end of my simulation, if I actually go down to high res geo, which is this first output, we'll notice that the name attribute is now my box. So because we've created this name attribute, Houdini will use the name attribute we've created for our simulation. And the simulation is going to work exactly as expected. And even on the sim point here, we are going to have my box. So the name attribute is now set by me intentionally right here. So if I disable these, there will be no name attribute incoming. And if I look on my high res geo, there will be a name attribute created by this solver for me. So this is one of the things I'd mentioned, that this solver does a lot of the stuff for us if we do not do it ourselves. But right now, this piece 0 here, and on my sim points, I'm going to have a piece 0 name. And on this transform pieces, even though this high resolution geometry does not have a name attribute, it will, in this case, because there's a single object, still work for this transform. But what I should do is my name attribute here on my incoming object. So primitives here and primitives here. And then I can see on my sim points, I've got the same name attribute on the actual points themselves. So this name attribute is used mostly, actually for really all simulations, we should create this ourselves. So it's very important because if we don't do it, Houdini will. But it's also used for transforming high resolution geometry, in this case the cube, to the points of our simulation points. So once we have hundreds or thousands of objects, knowing this name attribute and keeping it organized is going to help us make sure we get the correct objects to be copied to the correct simulation points. And if we don't create this name attribute, so in this case I'm creating it here on the primitives. So right now I've got a name, creating my box or naming it my box and setting that on the primitives. If we don't create this for us or ourselves, Houdini is going to do it for us. And the way Houdini does it is it does the connectivity of objects. So in the same way, if we added a connectivity node, Houdini would go through one by one, and in this case, assign an integer to every individually connected object. But that is what's going to happen inside the bullet solver if we do not create this ourselves. One more thing about the name attribute is usually it is on the primitives, but this solver does work if we set it to points sometimes, but good practice is to make sure the name attribute is always on your primitives unless your geometry is packed, which we'll cover in the next example. But in this case, we've got unpacked geo, unpacked proxy geo, and in this case, actually unpacked collision geometry. And it is all simulating and working correctly. And because we've got this name attribute here of my box, that is also being brought through and is working as expected. And the nice thing about this one is we can actually do whatever we'd like to this geometry here. So if I did a remesh here, maybe with even a decent amount of geometry, maybe 0.1, and a mountain, just to give it some different shape, maybe 0.1, whoops. I accidentally hit enter to go inside the mountain, but I'm gonna hit U to go up. So in this case right now, I've modified this high resolution geometry. And because all my name attributes are set up correctly, that will still be transformed to these sim points. And if I disable this sphere, right now the geometry actually used for the simulation is going to be the proxy geo. So depending on what we have for our proxy geo, that's going to be our simulation geometry, and we can visualize that by going under visualization, geometry, show collision shapes. This collision geometry here is if we want to visualize the grid, or in this case, anything that's connected to the fourth input. So we'll get to more of these settings in a little bit, but that is the fundamentals of the name attribute. You always want to make sure you have it. It should always be on your primitives, and if you don't create it, then Houdini will create it for you. So always be aware of that, because it's going to be really helpful as we start working on more complex setups. So awesome. That's going to be all for this example. In the next video, we're going to take a look at this example 3, and we're going to get a little more practice with the name attribute and also introduce the idea of packed geometry. So awesome. I'll be right back, and I'll see you in just 1 second. Welcome back, and welcome to example 3 for our name attribute and packed geometry section. In this video, we're going to get a little more in depth on both packed geometry, non-packed geometry, and then we're going to explore a little bit our name attribute on both the primitives and the points and packed. So really we're going to get a lot of practice on what's going on when our geometry is packed, why that happens, and how to make sure we know what's happening. So very similar setup. I've got a box here. In this case, I create a line because I want to copy a few boxes to the line. And the way I did that was a line here, 4, 1. So I place it along the z-axis, or excuse me, actually the x-axis. Move it up. I resample to add a few more segments. You can see right now there are 5 points. And then I randomize a normal just to give me a little bit of a random orientation for each of these boxes, excuse me. Right now, if I just did a RBD solver here and click play, everything would fall to the ground. So a nice handy thing built in for this solver is if I go to settings here for collision, ground collision, I can enable a ground plane. And now if I click play, Houdini has created this ground plane for my simulation, which is a nice handy way so I don't have to create collision geometry for every single one. I'm going to delete this solver because this one down here is actually the exact same. If I look down here, I've also got collision set to ground plane. And there we go. And this actually we do not need. So this collision geometry, this is the 4th input here, which we will learn about in this one down here. So in a little bit, but this is not going to be important for us now. That's only if we have stuff connected to the 4th input. So we've got a ground plane here, and this is working exactly as expected. And the other thing you might notice here is if I look at these, if I look at these points here, or these objects, there are a bunch of points, and there's no actual name attribute for any of these. But if we look at the resultant, or the output of our simulation, we will notice actually that there's piece 0, piece 4. If I middle mouse button, we can actually see there are 5 unique primitive string attributes for my name. And the reason for that is Houdini has gone through and created it for us, which is what we have covered in the last one. So in this case, if there is an existing name attribute, we'll use the name attribute to pack my geo. And if there's no existing name attribute, it will use connectivity. So the input to this is unpacked geo, and the output is unpacked geo. But if I did a pack node right here, and click play on my simulation, we actually will notice that these are all simulated together, which is another thing we will learn. I think this example was set up for this one here, but we could introduce it now. The idea is that if points or if objects share the same name attribute, they will be simulated as a single piece. So I can delete that. If I wanted to, I could create a connectivity here, and I could manually create a string. Instead of class, I can name it name. I can name it my box. And now I've got my box 0 through 1, 2, 3, 4. And if I look at the results of this simulation, we'll now see Houdini uses the name attribute that I had created. And if I disable this, it still works as expected because inside this solver, it is actually doing the exact same thing here, but the name attribute it's creating is piece. I believe it's actually piece because I think it's using the assemble node inside. Inside this one, I think it is the assemble node, which is a nice handy node that can create the name attribute, and it can pack our primitives for us as well. So right now I've got this little bit of a normal artifact shading here. So to get rid of this, I like to switch it to flat wire shaded. But now in this one, this will actually work the exact same way. And there we go. And this output attribute is now packed geometry. In this case, packed fragments. If I change this output prefix to my name goes here, this is going to be the prefix for the name attribute. And then the result of my simulation here is going to have that same name attribute. And then this packed primitives is how Houdini assigns, each of these objects to packed primitives. And then packed fragments are actually very similar to packed primitives. And for what we need now, we will leave these as the default. There are some distinct differences, but for most cases, I think both primitives and fragments will work just the same. So there we go. We've got that working here. So I'm going to delete this one here. I will delete this assemble node. And then on this same exact one here, I actually did a connectivity, which is what I had just done a second ago. And then in this case, I can pack my geometry here. Whoops. So I've created the connectivity attribute, or I've actually used the connectivity node to create a name attribute. The prefix is my string. So now, is my box, and it is a type string. So my box right here, this is my box name. And now if I pack this geometry, what I can do is, if I just use a default pack, it will merge everything into its single point. So right now it'll pack everything in one single piece of packed geometry, which would now make my simulation consider all of these as the same object. But what I've done on this node here is I've just checked the name attribute here, which would go through, and for each uniquely named attribute, it's going to pack it to its own piece of packed geometry. And now if we simulate, these will all be unique as well, because they are now their own individual pieces of packed geometry. The other thing to note about this one is the name attribute can be packed inside the geo. So in this case right now, I have a name attribute on my primitives right here. I pack the geometry with a name attribute here. And what this is doing, it's saying for each unique name attribute, create a unique piece of packed geometry. So 5 points, 5 unique name attributes. But what's now happening is there is now no name attribute visible on any of these points here. And if I simulate, it'll still work fine. But if I look at this, the name attribute is now piece. So instead of my box name, Houdini has read this as if we had no name attribute, because actually this is inside the packed geo. So we're not going to worry about this actually yet. But if I did an unpack, we would now see that back. So I would see that name attribute again, because our geometry is now no longer packed. But the important thing is, if we want to consistently keep this name attribute, so my box name, throughout my simulation, so right now piece, what I have to do is I have to make sure I transfer this name attribute to my points, which in this case is on the primitives, and in this case is not on the points. And if I play, it'll work as expected, and the output of the name attribute will be my box name. So we'll carry that through. And actually, if I do an attribute promote, I can go here. The name attribute is now on primitives. I can take it from primitive to point and promote that one. And now in this right here, I have the name attribute on points with packed fragments, which is packed geometry. I can simulate, click play, it'll work exactly as expected, and now on the output, my name attribute will be on points. If I use the assemble node here, what this will do, this will actually create the name attribute on my points. So the assemble node in this case is the same as a pack node and a name node promote. But it is helpful for us to, or actually, excuse me, the assemble node in this case is the exact same as if we did a name attribute, or if we created a name attribute with connectivity. So because I mentioned, I will show you exactly right here. So right now I've got this null. I've got unpacked geometry here, which are these points. If I create a connectivity attribute, or use a connectivity node to create a name attribute, and I want it to be a string, I'll create it on primitives, which right now is my box. So I'm going to Control C, paste this. I now have it on primitives, and I can use a pack node to pack by unique names, and we will now have currently no attribute visible, but if I transfer the name attribute, that will now be on my primitives. And for connectivity, if I set this to point, it will not create this same packed. So the way I'd have to do the same thing is connectivity on primitive, have it here in my primitives, pack it, and then do an attribute promote to get it from primitives to points and name. And now if I do a switch and a null, which is just a quick way to show you that this is going to be the exact same result. So no difference between these two use cases. The assemble actually is a little bit helpful because we can do it all in one node, and this can create it for us and be very helpful as we get more complex setups. And then this also would work as well, simulated. So I'm going to Control Z to show you here. If I connect this one in, this will simulate exactly fine, and this one will also simulate in the exact same way. I'm going to pause. I'll delete these two nodes here just to clean it up a little bit. And then one more thing is packed fragments. If I uncheck that, it will simulate as well in the exact same way. And then with the name attribute here, if we have the name attribute on our primitives, through the simulation, it will keep that consistent name attribute. But if we did not have it packed, so if I did not transfer this, the name attribute would no longer be visible. And what happens is Houdini is going to recreate a name attribute for us. So if I select this node here, we can now see a new name attribute has been created for us. And that happens whether or not the geometry is packed. And it still simulates as expected. So to recap, the important things to note is that the SOP solver here does handle both packed and unpacked geo. So in this case, we had our unpacked geometry. And then in this case, we had our packed geometry or packed fragments. It actually does handle both packed fragments as well as packed geometry. And for now, there's no distinction that we have to worry about between the two. And then we always want to be intentional whether we're using unpacked geometry here or packed geometry here. So whether we're using packed or unpacked, we need to just be aware of which one we're doing. And then for the name attribute, if there is an existing one, Houdini will respect that. But if there's no existing name attribute, then it will use the connectivity to create that for us. And actually what I could do here is quickly show you. So right now I've got this one here, just my solver. If I click play, whoops, I'm going to uncheck this display flag just so I do not see those. If I click play, all 5 of these cubes are unique pieces. So they're all going to simulate individually, because they are not connected, if I did a fuse SOP, which lets me merge nearby points, I can select this node, increase the snap distance, which eventually will snap some of these together. Now, because these points right here are connected with this fuse SOP, if I now simulate, Houdini is going to consider these part of the same object because they are connected. If I increase this fuse SOP or increase this distance, now every single piece is connected. And now Houdini is going to simulate these all as a single piece. There we go. And we can even see on our output, we've got piece 0, and that's the only one. We've got one unique name. And that's the same matching name attribute as our point. And we can see in this case, right now I've got 4. So 4 pieces here. I play. There's 1, 2, 3, 4 pieces there. And I will actually now have 4 simulation points. So every unique name attribute that's created is going to have its own unique simulation point. So that's another thing to note. So awesome. I think that's a good recap of this section here. Lots of this stuff is going to be more important, but definitely understand this as we're going because it is a little bit interesting. Does get a little bit weird, but I promise you, if it doesn't make sense yet, keep working through it and it will make sense. So that's going to be all for this example. In the next video, we are going to cover this next example here and we're going to keep learning. So awesome. I'll be right back and we'll keep going. All right, welcome back and welcome to example 4 for the name attribute and packed geometry section. So in this one, I wanted to share a quick introduction to how that objects that share the same name attribute are considered part of the same object by the solver and are thus simulated as a single piece. So this becomes very powerful as we stay organized and can even help us do some really handy connections between objects just by properly leveraging this name attribute. So by staying organized, we can do some really cool stuff. So this is very similar to what I had in the last one. Just a box, a line here. I moved it up, resampled to add a few more points, randomized the normal for all of these here, and then copied the box to these points. This one I actually did rotate just to give a little bit more of a interesting simulation. And in this case, actually, whoops, I'm going to do a bullet solver and I'll show you again that this is the default solver just with a collision ground plane enabled. And there we go. We have no name attribute, so we've learned before that Houdini will go through by connectivity and create a unique name attribute for each of our connected pieces. But now if we manually create our name attribute here, we can create a single one, in this case, using a name for every single piece. So it's all right now my box. And if I simulate this, it will simulate this as a single piece. And actually I could plug this into this solver here, and that would do the exact same thing. So all of these bullet solvers are the exact default solver, and if I did change anything, I will let you know. But what we could also do is instead of having this name attribute here be unique for, or excuse me, be the same for everyone, if I did the connectivity attribute again, string name, my name, here, right now it is on point, and we'll see that here, so name on point. I'll connect this to the solver and we'll see what happens. So these are all simulated the same, and the attribute is now my name 0, which I did spell incorrectly. So we should typically have our name attribute on primitives, but this solver does handle both point and primitives. You really should not have any mismatch. So always have it on prims, and you should be good to go unless your geometry is packed. So whether or not they're the same name attribute lets us have single pieces per object. And what we could even do is for these right here, I might even do, I'm going to quickly do another box. Actually, I'll do another 2 boxes just because I want to do one really fast example. So I've got a box here. I'm going to move it up. And instead of creating it again, I'll just transform it. Shake to disconnect this one. I'm going to merge these here. Now this 2 here are the 2 boxes, and I'm going to merge these as well with this geometry. So right now I've got 5 boxes with no name attribute. And if I click play when my simulation is set, we'll now see there are 7 individual objects. And I can tell because I've got 7 unique name attributes on the outcoming geometry, and I've also got 7 simulation points. But what's happening now is if I connect this here to the name attribute, or connectivity for the name attribute, it's going to generate a name attribute for these objects. And we can simulate and see what happens. Right now, even though there's these other ones here, these objects on the right-hand side do not have a name attribute. And these on the left-hand side do. And if I plug this into the solver, we'll now see that only the ones with the name attribute are being correctly simulated. If I disable this, none of these have a name attribute, and Houdini is creating it for us. Because on this output, I now have a piece. What I could do here is, if I wanted to have these all correctly simulated and I wanted to create the name attribute myself, I would either have to move this connectivity down here, in which case I now have 7 unique name attributes and 7 unique simulation objects. Or what I could do is connect it here. I'll have my name 0 through 4, duplicate this connectivity and connect it here, in which case I'll have my name 0 through 1. And if you remember the introduction, or remember one of the lessons from a few minutes ago, objects, I guess in this one here, but objects that share the same name are considered part of the same object. So right now, my name 1 on this object here, or this geometry stream here, and my name 1 here share the same name. So we can expect that they will actually be considered part of the same simulation object. And if I go down here and click play, we'll see that is the case. And instead of 7 points, if I look here, I now have 5 points, because that is 5 unique names that I have on my incoming geometry. So if I wanted to fix this and have these name attributes created independently, or created on separate geometry streams, I could just name this a different prefix. And now I've got my name 0 with an underscore on the right-hand side and no underscore on the left-hand side. And there we go. Another thing that I could do is I could recompute or regenerate a name attribute here, which will now create 7 unique name attributes for this one here. So if you are creating name attributes yourself, make sure you're not accidentally doing the same name for 2 different objects. For simple cases such as this one, it really isn't that big of an issue because it's easy to see. But for other ones in more big and more complex scenes, it might get a little bit confusing and difficult to debug. And I'm going to ignore this error. I think if I reset the node, it does disappear. So I'm not exactly sure why that's there, but we are okay without worrying about that. So again, this becomes very powerful as we stay organized, and we can combine this to do specific things, which are going to be very helpful. So awesome. That's going to be all for example 4, and then I'll be back to look at this one in the next video. So awesome. I'll see you in just 1 second. Welcome back, and welcome to example 5 for name attribute and packed geometry. In this section, we're going to do a very small, very quick extended example for example 4, and we're going to do a recap a little bit into how the name attribute can be on both primitive and points, and the solver here, the RBD Bullet solver, does accept both of those. So this is a very similar setup. I've got my box, my line, my objects, my points. I won't cover this again because that is pretty typical. I moved this, and this one here, I create a name attribute, my box, which right now is here. There's 4 unique ones, and I do the same thing here for these 4. So if I merge, we'll now see 4 unique ones, and which we did cover in this last section. These objects that share the same name attribute will be simulated as part of the same object. So if I connect the bullet solver here, go to collision, ground type, ground plane, and click play, I'll now have 4 objects, 4 simulation points, and 4 unique string name attributes. So I'll delete those here, but what is, oops, it froze, but hopefully, okay, there we go. What's important here is that if we pack this geometry here, we now have this name attribute on the primitive. And if we use the assemble, we now have the name attribute on the points themselves. So right now on this pack geo, or in this one that I use the pack node for, it's on the primitives, and this still works as expected. For the assemble node, on this one here, it's actually on the points, and this is still working as expected. And in this case, I assemble it, and I can promote it from points to primitives, and this still is working currently as expected. But let's maybe actually try something different. So what I'm going to do here is I'm going to make one more new example, and I want to try one where it is half on the points and half on the primitives. So the way I'll do that is I'm going to take this top one here, I'll pack it, and I'll pack, whoops, I'm going to alt drag to pack this one here. I'm now going to merge these two. In this case, this is essentially the same as this one here, but we will notice actually that these are now 7 unique objects, but they do share the same name attributes here. So I'm going to alt drag this solver, and we'll now see what happens here. So these are now simulating in a way that is not currently expected. And I actually believe what is happening here is the first match here for my box, because there's duplicates on the packed geometry, they are being matched to the first match they find for a name. So this won't give us the expected results. But what I was going to try to do, attribute promote, I'll quickly do this, then I will try to explain this a little bit more. So I'm going to go points to primitive, or actually primitive to point, excuse me, primitive to point, and I want my name attribute. So I've got my name attribute on points here on this left side. I've got my name attributes on primitive on this right side. And here on this merge, I now have a name attribute here, empty name attributes on this primitive, and points, and then empty on the opposite for points. And if I simulate, again, what is happening is not what we would expect. These are being simulated as the same object, but I believe their transforms are being driven by the first matched object. So in that case, actually, this is kind of interesting. If I have the top ones here on this input, so right now this top ones are being merged first, which means the point numbers are being switched. If I switch this Shift R, so if I select this merge and hit Shift R, you can see right now the order of this merge is being switched, in which case the point order of these top and the bottom ones are being flipped. So depending on the order of that merge, if I click play on my simulation, right now we'll have the bottom ones collide. If I switch this one, we'll have the top ones colliding. But the bottom ones are still being transformed based on the position of that top one. So this is really just an example to show you that you should not have them on both the points and the primitives. I'm going to delete that, Shift R, and now in this case, you can see we're also not getting what we would expect. And an easy way to fix this would actually be to either pack after these have been merged, or what we could do is we could make these unique name attributes for us to have them as separate objects. So if I did a I'll do a primitive wrangle just to make this example complete. So a prim wrangle here, I'm going to say s at name plus equals underscore. And what this does is this now appends this string to my name, in which case I will now have 8 unique name attributes. And 8 unique objects. The other thing we can explore and see what happens if I do an attribute promote here, then I take my name attribute from primitive, to points, and click play. We'll now see again that is not working as expected. So in this case, we don't want duplicate name attributes here because that is not working if these are not packed. That works a little bit more expected. So always make sure you're doing what you are expecting to do and do your organization in a way that is intentional. This hopefully wasn't too weird of an example, but make sure you kind of understand what's going on. And if you are getting weird behavior, maybe reset your organization into a way that makes sense, or maybe reassign your name attributes in a different order. But then again, the primitive and the point attributes for the names can be accepted by this solver, but mixing them is not a good idea because it will give us unexpected results. And actually now I'm a little bit more curious into why this was happening the way it did, so I might explore that a bit. But do definitely practice and keep working with those. So awesome. That's going to be all for this example. A little bit of a sidetrack there, but we're going to keep going in the next one and actually go to the next section of active attributes. So that's going to be another important one as we continue practicing our simulations. So I will end this video here and I'll be back in just 1 second. A quick extension to this one. Apologies for the confusion. I wanted to explain 1 more second why this was happening the way it was. So currently if this geometry is unpacked and I have matching attributes for the name for both of these objects, whether that name is on the primitive or the point, what happens when I simulate here is it is working as I would expect. And if I have that on the primitive, it's working right now. And then if I also have that on the points, we should see that that is also working as well. If this geometry is packed before, so if I pack this myself and then feed that into my solver right here, so I've got this name attribute on the points, but it is currently packed geometry. What will happen in my solver is it's not working the way I would expect. If I do a Shift R and switch this order, we'll see it also doesn't work the way I'd expect, but it works in a different way. And the reason this is because, or the reason for this is because the bullet solver inside here, and if I double click to jump inside and go up one layer, this solver itself, it does need packed geometry. And it needs to have unique name attributes for each piece of packed geometry. But if I do not pack this myself, side effects and Houdini and this tool itself here is correctly packing my geometry for me. So it's handling that for me in the way I would expect. But if I try to do it myself by packing here, Houdini will assume I did it correctly and it will not fix my repacking. So it won't repack this in the correct way because it's going to assume I did it the right way, in which case I didn't. So the bullet solver does require packed geo. Whether we pack it ourselves, we have to do it in the correct way. And if we leave Houdini to do it for us, we might have it do it the correct way and we might not. So that is a little bit more of an explanation, hopefully, for why this works. But definitely play with it yourself. Ask questions if you do have any. The packed, the names, all this stuff is a little bit confusing, but I promise once it does make sense, it definitely does. It does click. So that's going to be the end of this little extension. And in the next one, we're actually going to go into the next section. So that'll be all for now, and I will see you in just 1 second. All right, welcome to the next section of this RBD introduction series here, which is the active attribute. Now in this one, we're going to take a look at the active attribute and learn some fundamental things for it. But what we've got here is actually a little bit of a Houdini bug. So I wanted to leave it in the video just because it might happen to you. But we're now selecting objects and we're getting this ghosting that we wouldn't expect. So if this ever does happen, we're just going to do new pane type, viewers, scene view, close out our old one, and then relink 1 to 1 to 1 to make sure we've got our correct scene view. So if you're doing these simulations and something is not looking as it might look, then maybe reset your scene view just in case it is a bug there. But to get back to the lesson, what we're going to learn about now is the active attribute, which is an integer attribute, usually placed on the points. In this case, I'm showing you a couple examples here, but it is an integer attribute on the points that lets us control whether or not an object is active in a simulation. And by active, it means whether forces in the simulation will really affect that object. So an object can still be a collision even if it is not active. And we will learn that in this section. So I've got this sphere here. I do a copy and transform. Oops. I'm going to zoom back in here. And this is now duplicating this sphere 20 times up along the y-axis. This assemble node here is packing our geometry, in this case, into packed primitives, but we could also do packed fragments. So by default, it will do packed fragments. So I could leave that checked. Either one would work fine. And what I'm also doing is I'm now creating a name attribute, and it's creating that for me, in this case, by connectivity. So now I've got 20 unique name attributes for the 20 times I have copied this here. Another way to create this one would be to do a name with connectivity, which we've done in the past right here. So I won't show you that because I want to stay a little more intentional and on our topic as we go. So right now what I've done is I create an active attribute. So I at active equals 1. If I look on my primitives, we can see that here. And if I use an RBD solver, this is not the correct way to do it, by the way. We should put this on points. But I'm going to go to collisions, ground type, ground plane. And we will see this. And this simulation works in the exact same way that it would if I did not have an active attribute. Because by default, these objects will be considered active. But now if I had this primitive, maybe one set to 0, it'll still work because it should be on points. Now if I set this active 0 on points, these will no longer be active. The reason this was on primitives is because as I was creating some of these, I was going back and testing stuff. So, whoops, this should have been points. So I do apologize for that, but definitely keep your active attributes on your points. So this is set to active of 1. These objects now are active in our simulation, so they can be simulated. Which is the exact same setup I've got here on this left side. What I can also do is animate this active attribute. So in this case, I've created a little expression which now says if the object's position is less than this float, which I've animated over time, then set these points slowly to active. And if I color based on active, we can now see this active attribute is being set slowly up here as we're animating through this. And now if I simulate this here, because this active attribute is also on our points, what's going to happen is as that active attribute is set to 1, the object will be simulated. And this is actually important. By default, it is set here for override attributes. If I uncheck this here, that won't be updated per frame. So it will show the coloring, but it won't actually update this inside the simulation. So by default, this is checked on, and if we need to change other things in the simulation, which we will later, we might have to change the attributes that are being overrode here, or overridden here. And there we go. And then this example here is, I believe, actually the same idea as this. So that really is the way we set up our active attribute. That's going to be the end of the first example here, but I will actually show you one more thing. It does work as well if the geometry is not packed. So right now, I've got a primitive attribute for name. My points are not packed. And I can see that by zooming in here and middle mouse buttoning on this one. I see all my points here, no packed geometry. I still create this active attribute. And in this case, I'm going to preview this one here just so I can see the color. And we'll now actually see, as it's being simulated, these objects are now working as expected. So even if my input geometry is not packed, they are working as expected. And we can zoom in, and I believe this might actually be, well, somehow this is being transferred to our packed geometry inside this solver. But whether or not we choose to pack it, that point attribute should still work. Oh, okay. Actually, I do remember why I set this example. So in this case, I've got my active attribute set here on this left one. It's slowly being animated. And then everything stays active. What you can also do, which I did on this case, is I animated all these the attributes, I animated them to be active, and then I set another keyframe here that would then change them to be unactive. So with that active attribute set back to 0. And we can see as this goes through, if I simulate this here, my active attribute is going to be set and these points are going to be animated, or excuse me, these points are going to be simulated. I want to be intentional with my use of animated because that is another attribute we'll learn about. But as they are now set to blue, or as the active attribute is set to 0, those will now freeze in the simulation. And we will notice, maybe not in this case, but attributes or objects that are not active, so have an attribute active or an active attribute, set to 0 can still be used as collisions, which is actually this next example. So I'm going to end this video here. We'll get into the next one, and hopefully I can enunciate a little bit better as we keep working because there's lots of words to be said. So awesome. That's going to be all for this section. And in the next one, I'll be back to cover this next example. Welcome back and welcome to the next example for our active attribute. In this section, we're going to get another example here for how objects, which in this case the cubes, and I'm getting my normal shading here a little bit funky, so I'm going to switch this to flat wire shaded, but how cubes, or these cubes here in this case, can be set to active of 0 and still be used as simulation objects or as collision objects. So this one, I've just got my cube here. I transform it up once, twice, a second time, and 3 times, a little bit taller. And I actually choose to assemble these into packed geometry, and I'm also creating a primitive attribute as well. So we've covered in the past that you don't necessarily have to do this yourself. The solver might take care of it for you, but as we get more complex setups, my preferred way of working with this SOP solver is to be a little more intentional with how I create my packed geometry, because then it usually works a little bit more expected. So what I've done now here is I've set my active attribute on my points, which in this case are packed fragments. And we've covered whether you do, I'm going to reset this to its default value. Whether you do packed primitives or fragments, there is no difference between the two, at least for now. And here we go. I've got these all active. On this one actually here, I do animated from 0 to 1 on frame 73. And then what I've got here on this right side is actually a fetch node or an object merge that fetches this node right here. So this we covered in the last section, but this was just points, actually packed geometry here, so packed fragments that I am slowly animating up to be active over time, and I've previewed that active attribute with a color node. And I'm actually going to use this, I'm going to reuse this actually quite a bit in future examples, just because this is a nice, handy way to showcase some of what we're doing. This comes in here. The nice thing actually about packed geometry is because it's points, what you can do is you can use point jitters, you can use mountains to actually displace these. So I could disable that and enable animation, and then that will displace in a way that might be handy. So there's tricks we'll do on future projects for packing and unpacking geo. But now I just transform this up a little bit, and this animation still is here. I'll merge these together. Right now this is giving me a warning on the color attribute, which is on this side. I'm going to ignore that now because in this case it doesn't matter. If I click play, we'll now see these cubes as they are being set to active are falling down, and these spheres are actually working as collision. And then we can now see this top cube, which if I actually did a duplicate for this color here, maybe actually I'll do it for all of these. So this top cube, once it's set to active, it now joins the simulation, just as you would expect. So this animating of active of 1 to active to 0 is a way you can have objects be involved in a simulation and then join and rejoin at later times. And the important thing to note is that non-active objects, so objects with the active attribute set to 0, can still be involved in collisions. But as we do that, we actually will want to be aware of collision shapes, which we will get to in this section down the line here. But as we're looking at these objects here, we can visualize and show collision shapes. So in this case, it's just animated at frame 73. And a very simple example here, but this will be very important as we keep learning. And then this on my properties, override attributes, this has to be checked for active, which by default, this is already included. But if I go back, this will update correctly and the active attribute will actually be transferred through the simulation, but my attributes will not actually be used in the simulation. And actually the reason they're being transferred here through is because this high resolution geometry internally here, this node is using a transform pieces to copy my high resolution geo, so this one here, to the sim points. So even though those are not being used in the simulation, the attribute is still coming through from my sim or through this node. So it's not technically used in the simulation, but this node still passes through the data. So we want that checked, and we would get exactly what we would expect. So really that's all for this section in this example. In the next one, we're going to do a little bit more about this falling on cubes, but I'll be back in the next video to showcase that. Welcome back and welcome to example 3 for active attributes. In this section, I'm going to introduce the general idea that if we have no intent of adding a cube or adding a collision object to the simulation, we can use collision geometry instead of what we did in this last one of setting objects to inactive or setting their active attribute to 0. So on this left example here, I had this cube join the simulation at this frame 73, and we can see its active attribute is set to 1 on that specific frame. But if I wanted the same result here with my objects, but I had no intention of one of these cubes joining the simulation, I could use this 4th collision input for collision geometry. And then that would be simulated in my object or simulated in my simulation, but wouldn't actually be involved in the simulation itself. So there'd be no chance for me to set this to be simulated. It just works as pure collision. And the nice thing about collision is we're not going to get that out through our high resolution geometry. So if we did want to visualize that later, we would have to remerge that with our collision geo. And we'll get exactly what we would expect. So depending on whether you want to do just collision or if you want to have objects join the simulation later, you might choose to do either collision geo here or set them to be within the simulation but just set with an active attribute of 0. That's actually all, that's all for this section. We'll be covering the next one, but this is a nice fundamental idea that we'll want to keep in mind as we start planning our simulations. So awesome. I'll be back in the next one, and we're going to get started on the next idea of collisions, which are going to be animated versus deforming. So awesome. I'll be right back. Welcome back, and welcome to the animated attribute, or welcome to example 1 for this animated versus deforming attribute section. In this one here, we're going to take a look at the animated attribute, see what it does, see how to use it correctly, and then learn a little bit more about the specifics of how it works. So at a really high level, the animated attribute, and I'll explain this quickly and then we'll see exactly what's going on. The animated attribute tells the solver, in this case our bullet solver down here, to update the position of our collision objects at each frame. So what it's doing is it's taking a animation from outside the simulation. So in this case, we've got this moving object here, these cubes, and it's going to bring that into the simulation and let this animation interact with the objects that are actually being simulated. And then the deforming attribute, which we'll also learn, does a very similar thing, but the animated attribute only modifies the transform of a object's collision mesh. The deforming object updates the transform of the object's collision mesh, as well as recooks the actual shape of that mesh, that collision mesh, on each frame. So that'll be helpful if the actual geometry itself is animated rather than the position or the transform of the geometry. But to explain this, I've got this set up here. This is very similar to what we've seen before. I've got a box, transform, so move these up. I assemble these, in which case I am using the assemble to create a name attribute as well as packed primitives. And in this case, I've left it on the default for packed fragments, which is fine for us to do now. I now create my point active attribute set to 0 for these two. And then for this third one, I do animate that to 1 on frame 73. And what I could do as well, actually, is I'm going to do a color node. I'm going to move this a little bit down, but I'm going to color this animated, and you have to set yours to ramp from attribute. And I'm going to flip this just so it matches the incoming sphere geometry that I've prepared in a previous section of these lessons. What we've got here is just these spheres slowly being animated to active, and these are actually packed fragments. This point jitter is displacing the position of these objects, and because these are packed, this jitter is not displacing the actual spheres itself here. It's treating these as a single point. So it is displacing the position of the entire sphere instead of these individual polygons on our sphere. This transform is just moving it up. And I've got this noise here, which is a attribute noise set to modify the position of these objects. And then again, because this is packed geo, it's moving the entire object at once. If this geometry, was not packed, so if I did not use this assemble node, then the mountain or this attribute noise would be displacing the individual polygons of my cubes instead of the positions of the entire cube. I've now created an animated attribute here on these cubes, and I merged that with this object here. I am getting a warning about my animated attribute not being matched. So this, I believe, will actually still work correctly, which it does. But perhaps what we could do is, for better practice, set our animated attribute on these points to be 0. So we're not getting that warning, anymore. And it will still work the exact same way. But we'll see, actually, once we have our object here. I wanted to actually set this to, I'll leave that actually connected here. I wanted this set to active, not animated. Whoops. Because I want to see this cube red once it becomes active. So now what we've seen here is this cube, when it's set to active, is now joining the simulation as it did in the past. But also what's going on is well, first it's glitching a little bit out here because at the time it becomes active, it's inside the blue here object for this collision. So it's quickly being snapped outside of that collision mesh. But this animated attribute is still set to 1. But because it's active, it is being allowed to join the simulation. So in this case, our active attribute is overriding our animated attribute, which is an important thing to note. So although this is set to animated, the active is still allowing it to be within our simulation and work as expected. The other important thing to note here is the order of when we are setting this animation itself and when we're actually setting the animated attribute. So as we've learned before, this RBD solver works on packed geometry, and whether we choose to pack that geometry ourselves, as we do here with the assemble nodes, or if we leave Houdini the option to pack it for us. Now it's not working because there's no name attribute. So I'm going to uncheck create packed primitives, and I'm going to uncheck this mountain actually. And we'll now see this still works. So we are letting Houdini pack it for us, but we're not getting this animated attribute. And we can actually see this is not packed geometry. Although the assemble node is here, I have unchecked create packed primitives. So I could just use a name attribute to create this here. I could use a connectivity attribute, but I do need to have a name attribute because there is an existing name attribute on these objects here. And that actually is interesting. It looks like our simulation is still being used. So these objects are still interacting with our object. But because there's no name attribute, they're not coming outside of our simulation. So that is an interesting thing to see. But if I do give it a name attribute on my incoming geometry, this is still unpacked. We'll now see that our geometry here is going to still work as expected in the simulation. If I enable this position here, what's now happening is this animation will not be carried into our simulation because we would actually have to use the deforming one, which we will learn about in the next example, excuse me. But the thing I actually really did want to show you is if I do a transform so maybe I'll do a different, instead of a noise, which is deforming it, which is going to be a little confusing with the deforming attribute. If I do a transform here, I want this one on all three of them, and I'm just going to do a $F for rotation along the y-axis. I'm going to disable this attribute noise down here. So now what I've got is I've got these cubes rotating, so they are animated. So these cubes are animated, and the animated attribute is set to 1. But if I go to my simulation and I click play, we'll see that my cubes are not actually transforming within my simulation. And the reason for this is Houdini is repacking this geometry for me, and it's not transferring that animated attribute for me. So this active is still being transferred, but my animated attribute is not working the way I would expect. So this did get me a little bit confused, when I was first starting to use these, but now once you kind of understand this, you'll see. So if I did want this to work, I would have to have this as packed geometry. In this case now, these are packed fragments. The animated is set to 1. And we'll see this still does not work. And the reason for this is because our transform is happening before we've packed our geometry. So if we want this to work correctly, or work as we would expect, because technically this is correctly, but we just want to make sure we know what we're doing. If I take this transform and after the geometry has been packed, I then transform it, we can now see on my simulation, it is correctly being transformed. And the reason this is happening is because when the animated attribute is set to 1, what it does is it re-updates the transform of the packed geometry at each frame. And in this case, these are now here being animated, but they are packed. So our animation is not carrying through our actual, or carrying through to our simulation. So what we need to have is, if it is animating, we would need to have our animation after the geometry has been packed. And then that way our animating attribute, or our animated, attribute would work correctly. So either having this transform after would make sure it is working. And there we go. So it will take a while to get used to. If we did want to actually use this animation here, so this animation here before it's packed, we could use deforming in this case here, and there's ways we can set that up so it would work as well. But for now, this is the animated attribute to use, and that can be updated throughout the simulation by us. So I think that might actually be all for this section, or at least this example. The other thing maybe I'll quickly mention is the shape for animated will remain the shape of the first frame for the simulation. So if I had a subdivide maybe here that was set to 0, this is probably not a very good example actually, and then set to 2, for this one, what's going to happen is, although this is actually updating here, the collision on visualization, if you are following along, don't worry about this, it's going to be set on this first frame, and then once this geometry does update, it will not be updated. So that will stay static. And actually the blue is a little bit confusing here, but we can now see as not being changed. So we'll get more practice with exactly what's going on. That subdivision might not have made anything really more helpful, but try to understand this as we go, and we'll get more practice. So it definitely will make sense as we keep going. But that's going to be the end of this section here. And in the next example, I'm going to introduce our deforming attribute, and we'll learn a little bit more about how this is working. Welcome back, and welcome to the deforming attribute example. In this one, we're going to continue a little bit more kind of what we covered in the animated section, and then introduce our deforming attribute and hopefully get a little bit of a better understanding between the two and when you might use one over the other. We will get a lot of practice on this in this final section here. But for now, we are going to get started with the deforming attribute. So this setup is very similar to what I've done in the past. I've got a box, I've got a mountain, And actually what I do have here is a mountain on the unpacked geometry. So we have covered in the last section that the packed geometry, well, I'll get to this in a second maybe actually. So I've got this mountain here. I animate it, or I transform it, excuse me. And I transform the second one and a third one, and then I assemble, or I use an assemble node to create packed primitives, in this case packed fragments. Apologies for that quick cut, but I do use the assemble node to create my packed geometry. Packed fragments or primitives, in this case does not matter, but I have also created a name attribute as well. I merge those together. We can now see I've got this animated object here, and the important thing to note is that this animation is happening before the object is packed. And if I animate the positions here, we'll now see I've got two layers of animation. I've got a deforming noise on the actual geometry of the cubes themselves, and I've got a animated position on the packed geo. So this is now animating the entire object of the cube, and this noise up here is animating the polygons on the cube itself. And the deforming attribute here is now going to allow us to tell this solver to update the collision shape and the position of the mesh at each frame, and we'll see exactly what happens in just 1 second. So I now set my deforming attribute to 1 on the points, and I've got the same sphere example as I had on the right one. Spheres come in, point jitter to add a little bit of variation, and then I move those up on the y-axis. I'm also getting the same, or I was for a second getting the same mismatch of attributes for deforming for both of these, but it looks like that went away, and now it's back. So what I could do to fix this is I could go to deforming, set that on this cube, set it to 0, and that will fix it for deforming, but leave it for color and active. But I'm going to ignore those for now, because that might actually happen as we get into more simulations. But good practice would be to set it for both of those. So actually maybe what I'll do is I will set that, because once simulations get more complex, we're going to want to have it set for both of these. Maybe what I'll do is actually in this one, I'll do I at active equals 0. That'll fix everything except color. And maybe I'll do a color ramp from active. And I'll flip that so my blue is going to be the same color as my blue here. Meaning that active of 0 is blue and active of 1 is red, which is what I've got on this right hand side. Now if I merge, all those are fixed. We should not have any issues. Everything's packed fragments, which is okay. And now if I look at this, and if I disable this show collision shapes, we can kind of guess what's going to happen. So I've got here, well actually, let's just see what happens first. So right now, I'm getting animated objects, and I'm getting the deforming. And the reason for that is because I have my mesh set to deforming. If I just had this set to, I'm going to comment out this line. If I had this set to I at active, or excuse me, I at animated equals 1, this now here set to animated right now on this one and active of 0, I'll get this first layer of animation. So this is what we covered in the last video, or the last example. The animated attribute updates the position of each of these cubes' collision meshes at each frame. And if I do show collision shape, we can now see that these collisions are being updated at each frame and the position of them. And the reason they are now not looking like our object is by default, the collision meshes for these objects actually uses convex hull. which is a way to get no concavity in a collision mesh. So I've created this here as a quick example. So there's no concavity possible. And if I preview this cube and select my convex hull, that will essentially shrink wrap. And actually this is a shrink wrap node that will shrink wrap this object. And this is what's being used by default in my simulation. We will learn in the next section how to change the way we interpret our collision meshes. But for now, the important thing to know is that the position of this mesh is being updated when this animated attribute is set to 1. If I set deforming to 1, what's going to happen is the position is going to be updated, as well as the mesh itself. So now if I go here, I will see the animated object moving, and I will actually see this convex hull being recomputed at each frame. So it is changing its actual shape, and it might be easier if this was a different color. So maybe I'll set this to green just so we can see a difference in the blue. So right now green is the incoming mesh, so this incoming object. I'm now merging this here, and on this one, because under visualization I have show collision shape, we can now see the blue preview of my collision shape, which is being updated on each frame to actually match this incoming geometry. So that's the important difference between the deforming and the animated. So again, just the animated is only going to update the positions and not the actual internal animation for this noise here. So very important to keep practicing and be aware of what's going on. And this is how we have to make sure that our animation is done in the right order. So again, this deforming is done before it's being packed, because I actually want to change the internal geometry itself, and then the animation would be done on the packed geometry. In this case, packed fragments, but again, packed primitives would essentially work the same way. And then the convex hull here is how this bullet solver by default is calculating the collision mesh. And we'll learn in this section here how we can override that for each object to set multiple different ways to have it generate our collision mesh. So awesome. I think that might be the end of the introduction for the deforming attribute. In the next one, we're going to take a look at a little bit more of a similar idea, but we will get some more practice in that one. So awesome. I'm going to end this one here, and I'll be back in just 1 second. All right, welcome back, and welcome to the next section for our deforming attribute. So we have covered in, I believe it was a few ones ago, the idea that if we want to have our cubes, in this case, well, first, in this case, I'll actually show you what's going on here. So if we want to have our cubes be simulated in our object or in our simulation, and by simulated I mean involved in collisions, we can either have them set as active of 0 and plugged into our geometry input for the solver, or what we can do, I'm going to escape to cancel that simulation here, is we can also plug those into the collision geometry for our object. So these two ways of having the cubes in the simulation would likely depend on either how you want to set your simulation up, or if you did want to have one of these cubes break apart later and actually join the simulation, you'd want to use this approach here, where it is set to active of 0 and is actually considered part of the simulation itself rather than collision geometry. But the idea I wanted to mention, or actually showcase in this example here, is that for our collision geometry as well, we can also do a deforming geometry or deforming attribute to have our position or our transform updated for the collision mesh, as well as the actual geometry itself. And actually, as I'm thinking about it now, I did not have an example for this of animated, so maybe I will also showcase that in this section here. So what we've got here is our box. We've got a mountain, which is now displacing the actual cubes themselves. And it should be one box. So one box here. Mountain is displacing these cubes itself, or this cube itself. I am now transforming it up once, twice, and 3 times. And then I am using assemble nodes to create my name attributes. The important thing to note here is now we've got 3 unique name attributes and 3 pieces of our packed fragments. If I now set this here to deforming, and I'll disconnect this for a second, we will actually see on this RBD solver here, and I'm going to recreate a new one from scratch actually. And by doing that, I'm going to do RBD solver, bullet solver, because there is a setting here I want to show you that is sometimes overridden by yourself, or this deforming attribute can be set in 2 different ways. So I've got this bullet solver here. If I set my display flag on this one, I can actually now view this, and I'm now seeing this object, and it is not deforming and it is not being animated. And the reason for this is if we go to our collisions, we can see collision geometry is set to animated, and I've now got it set to, or excuse me, collision geometry, I'm setting it myself to deforming, but the incoming is now set to animated. So if I disable this deforming, leave it on animated, it still will not work because now there's no animation done on the packed geometry. If I connect this, which I will in a second, then it will make sense, or it will actually animate. If I set this to deforming, here on the collision geometry, which again is for this 4th input, we'll now see this is deforming as you might expect. And the nice thing about using this collision input rather than our geometry input for these cubes is by default, this now gives us a nice little setting. Whoops. I want to do show collision shape. Under collision, this now gives us settings to compute different ways we can actually have our collision mesh be generated. So by default, it was convex hull, but I could change this on my collision geometry to concave, and then I'll get a better representation of this deforming geometry, which could be exactly what I wanted. But I'm going to leave this, I'll actually leave it on concave for now. But the other important thing to note is that although I set this collision type here, so right now if I set this to static, none of this is going to be animated or deformed. But what I can do is I can set this deforming attribute myself here, and now on my solver, it will be deforming. And the important thing for that is if we want to have some collision geometry that's deforming and some collision that's static and maybe even some that's animated, we want to be able to set this one ourselves. So right now I manually set my deforming attribute to 1, and now in my simulation I can see it is deforming even though it is set to static. If I set this to animated, we will not get our deforming attribute anymore. So that is an important thing to note. If I disable this deforming, so now it is neither deforming nor animated, and I play this, actually let me enable this one here. So this P, this position here, is this attribute noise is just a displacement of the position, and because these are packed geometries, it is now actually displacing the entire cube itself. So I've got this bullet solver here. If I had this set to static, nothing's going to happen because it is static geometry. If I set this to animated, we'll now see the animation from this attribute noise is being updated on each frame. If I set this to deforming, we'll now see the animated object, so this one here, and this deforming attribute is being updated on each frame. So it's also recomputing, Houdini is recomputing the shape of this collision mesh on each frame as we continue. So whether you set it yourself or if you allow Houdini to set it for you, that is an important thing to note. And it actually looks like if I set it to animated, so here, but I am intentionally setting deforming as well, I'm not getting what I would expect. So it is neither animated or deforming. So if you do set these yourself, then maybe set it to static. And typically you wouldn't use a true value for deforming and for animated. You would either use one or the other. And this solver here on this side is the exact same setup. And you can now see if we select this solver itself, we see the collision geometry. If we go under here, visualization, show geometry. But because this is collision, this is not going to be passed through our solver. If we wanted to visualize these together, we would have to then merge our geometry after our simulation had been completed. But then the important thing to note here is that even though I'm merging this, this might be animated here, but if my collision type is set to maybe static for the simulation, it won't actually be moving. But for my merge, it'll be moving. So it won't give me what I'm expecting because I am now merging this animated geometry here, but my simulation is considering this geometry as static. And then this collision shape is very helpful as we set up this collision geometry ourselves. So we can do this as well for this input geometry for our actual simulation, but we'll be getting to that in the next section. But for now, actually, I think that's all for the deforming attributes, the animated attributes for both the objects. And then the decision, of whether you choose to do a collision geometry here or actually plugging it in to the main geometry would be up to you. And let me actually do a SOP or an RBD solver. So I'm going to delete these two nodes just to keep it a little more organized. I'm going to put this in the left. I'm going to plug this into my collision geometry. And I'm going to add a ground plane. And there we go. It is now animating. It is not deforming. If I set this to deforming, we'll see it is now set to deforming. But what I could also do is I could do a merge. I'm going to actually merge this one here Maybe I'll move it to this side just to stay a little more organized. But I actually want to merge it with this object here. And what I'm going to do is I'm going to connect these, both of these here, to this left side of the solver. And now I'm not getting my active attribute. So what I'm going to need to do is I'm going to need to create I at active I'll create it in this wrangle as well, actually. I at active equals 1, and I'm going to enable this wrangle. So now I've got my active attribute, or whoops, I want this to be 0 because I actually want this to be collision mesh. And by collision mesh, I want it to be not in the simulation. I want it to be colliding with objects that are being simulated. And now I'm getting the same exact result. But the important thing to note, if we do it in this case, is the visualization show collision shapes. By default, these are going to use the convex hull. And with just this solver, there's no way we can set that. We would need to use the RBD configure to set the collision shape, which we will do in the next section. And what we could also do actually, is set this to active of 1 and see what happens. So now our objects are receiving the transform from the deforming and they are being simulated, which could be what you want. In my case, I haven't really found a use for this, but it is interesting to experiment and see what's going on. And then the order you decide, again, your packed, unpacked, and then whether you set your deforming attributes on your packed geometry or your unpacked geometry is very important. But again, it should be a point attribute. And typically, I choose to work with intentionally packing the geometry myself because that is going to be a lot more scalable as we get into more complex and more intentional setups. So I believe that actually does cover everything for deforming, for this collision input, and even a little bonus of how to set it up for the geometry input as well. So that's going to be the end of this section. The next one, we're going to do a lot of actual interesting stuff on the collision shapes, and then we got plenty more to cover. So awesome. I'm going to end this video and I'll be back in just 1 second. All right, welcome back and welcome to the final section of this first section of our RBD introduction. This one is going to be a little bit more of a kind of practical example for kind of modifying a little bit these collision shapes. And we've got actually quite a few examples of setting these all up. There is one node here, which it looks like, okay, we are configuring. Okay, good. So we are going to be covering a lot of examples here. And then I might do a separate video for each one, just in case you want to use the scene files and come back at a later time to see a specific example. But we're going to get started in example 1. Again, this active spheres is something we have covered before. It is a row of spheres currently as packed fragments, and their their active attribute is animated from 0 to 1, and then the color is actually created to match that active attribute. So active points of 1 are going to be red, and active points of value 0 will be blue. This point jitter is displacing them because it is packed geometry. It is displacing them as the entire points rather than the individual polygons on our spheres. And I'm transforming this up just a little bit. So for here, what I wanted to showcase was this sphere collision object, which is actually going to be a bull, but I create a sphere, I clip it here, transform it to make it a little bit more shallow, and then I poly extrude with a distance of 0.2 to give it a little bit of thickness. And then I am using an assemble node to both create a name attribute, which I prefer to actually change from piece because it's a little bit more easy to see that I have intentionally created this myself. And it also packs our geometry. And now I am animating the packed geometry, which we have learned in the last section, is if I use my collision geometry of animated and I have an animation on my packed geometry, I'll now see this animation being carried through into my simulation. If this animation was before it was packed, this would still look correct. But for my simulation, even though this is set to animated, it will not carry that into the actual simulation. But now the important thing to note here is that by default, this collision geometry is set to convex hull. Whoops. I accidentally clicked this one, so I'm going to click it again to switch them back. But if I go to visualization, show collision shapes, not on the geometry here, but actually on the collision geometry, we'll see this blue object is what is being used as collision for my bowl. But what I actually want to do is set it to concave, which I did on this solver, but I will do the same thing on this one here. If I go to my collision geometry, collision here, collision shape, concave, and now I preview this collision shape. Whoops, I might have to reset my simulation here because I am now at frame 34, and this orange marker is letting me know that there are parts of my simulation that have not been cooked. So I'll reset, and now then correctly I am getting my new collision shape, and there we go. And now my objects are being simulated as I would expect. The same thing is exactly set on this solver. If I go back to the start, reset my simulation, and click play, we'll see it is again working as expected. So the important thing here is that because this is now set into the collision side, default and built into this solver, we have a menu for setting the collision shape of this object. And then again, the animation here is only working because the object has been packed before we animate it. If I actually had the animation before, this will not work. But if I had set this to deforming, we will now see it does work because it is now updating the transform of my packed geo and the collision mesh itself of the packed geometry as well. So always be aware of which stage and which where your animation is with respect to where your objects are being packed. And also, if you are letting the solver pack it for you, be aware of how that is all set up. So I believe that actually is going to be the end of example 1. And then again, that is the collision shape here we want to be aware of in our collision geometry. So I'm going to end the video here, and then in the next one, we'll be back for example 2. All right, welcome back, and welcome to example 2 for this example here for our collision shapes. This is actually, I believe, the exact same result that we had on concave collision here. So again, the exact same setup. I've got my object animated here, again, plugged into the collision geometry shape. Set it here. I can reset my simulation to clear the cache I just had. And if I click play, this is going to work as expected because I've got my collision shape set to concave. My geometry is set to animated because my pack is happening before my transform is happening. And I've got this handy little expression here I set to animate my bowl. So that is the exact same setup we had in the end of the last video. But just to be consistent with the scene file organization, I wanted to have a video for this one as well. So awesome. That's going to be the end of example 2. In the next one, we will take a look at example 3. All right, welcome back and welcome to example 3 for our collision shapes. In this one, the idea I wanted to show is that our animated attribute can be set manually on our packed geometry here, or we can be setting it inside the solver ourselves. So this is a topic we have covered before, but I just wanted to do a additional example to showcase this in practice. So we got the same exact setup here. Got our points, the transform, got our sphere, a clip, a transform to move it, and scale it down, a poly extrude, the assemble to pack and name my object. So my object, a transform here, and then in this case, I'm actually setting the animated attribute to 1, and inside my solver here, I actually do have collision geometry enabled, which is this 4th input, but I have this set to static. Now we have learned in the past that we can set these ourselves, and this will override this preset here. Only in some cases actually. So in this case, I've set this to animated and set this to deforming, and it is still not working. And the reason for this is actually let me actually try to explain this in a little bit different of a way. I believe what's happening here is technically the collision shape of the unpacked geometry, or the geometry before it's being packed, is not being modified. So I might do a mountain to set this. I'm now going to set this to 0.2, and I'll enable animation. I'm going to decrease my fractal to make it a little bit more of a smooth animation. So now I've got an animation on the unpacked geometry, which we would typically use deforming for. I pack my geometry. We can now see this animation still is visible here. I then rotate and transform this packed geometry, and I'm now setting an animated attribute on my point, which is packed fragments. If I go back to my concave here, if I set this to static, we will get the animated attribute here. So we're getting this second transform after the assemble has already happened, excuse me. If I go back, I set this to animated, we'll get the same result. And if I go back and I set this to deforming, what we're actually going to get is nothing, which is interesting, but that's good to know. Now if I go back here and set this to not be animated, we'll now see the deforming works correctly. So typically you would not have animated and deforming both set to true. In that case, this is what's going on. We've got our animated attribute set here, and now this is setting our deforming attribute. So typically if you are setting the attributes not within this setting here, you would leave them as static, and then whatever you have set here. So if I did I at deforming equals 1, I'll leave them both for now enabled. Nothing's happening. And I comment this out to now have it only deforming. I now see it correctly as deforming. Or what I could do is set this to 0. And there we go. So if you do have multiple objects that are deforming and animated and maybe static, you would want to set a false value for animated, and even what you would want to do is I at active equals 0. Because if you don't create a value for an attribute and you're merging it with another object that does have that attribute, very oftentimes Houdini will throw you a warning on a merge node, which we've had in some of the previous videos in this RBD section, but sometimes it will also create a default value for you. So it might create a cube, or maybe I'll show you real quick. If I create a cube, and this is just a thing Houdini does a lot of the times, I'm going to do a wrangle. I'm going to set I at attrib equals 1. Right now I'm setting an attribute for my points, and I'm doing it for all points here. If I set this just to 0, what's happening is I'm only setting an attribute on my point 0, but Houdini's giving me a default attribute for these other points. So maybe I will leave this as default attribute set. And maybe I'll leave a comment just to be consistent. So Houdini sometimes sets for you even when you don't set them yourselves. So this I set to 1, it's now set to 0. If I set this to 2, it's now set to 0. And if I did another attribute here, or another wrangle, maybe set it to 0.1, and I set my attribute to 1, we'll now see that is correctly set, but my other attribute is now still 0. So if you don't do this here yourself, setting these correctly, then Houdini might actually do it for you. And what we could see is if I do a merge, and I have a sphere, maybe, so some more points here, maybe way fewer, just so we don't have such a messy geometry spreadsheet. Right now this has no attrib, and there we go. So right now I've got my sphere set to 2 and 1. These points that I have not manually assigned an attribute now have it 0, and this sphere, which does not have that attribute set, when I merge it, Houdini will actually create a default attribute value of 0 for that missing attribute. So that's very important as we start setting up more complex simulations, or really as we set up anything in Houdini, being aware of what is done by Houdini by default is very, very, very important. So I would always set those. In some of the past videos, I hadn't done that, and we've learned that the solver sometimes does it for us. So we should be aware of what's going on and be intentional with how we work in Houdini, because that is the best way to work. So a little bit of a sidetrack there, but also not really, because this is critical as we're actually getting more in depth with really understanding what's going on. So awesome. I think that's going to be the end of example 3. And I'm going to pause the video, or cut the video actually. And then in the next section, we'll be back with example 4. All right, welcome back, and welcome to example 4 for our collision shapes and a little bit more of a practical example applied. This one is kind of a combination of 2 ideas we've seen before, but it's going to be important understanding what's going on. And then there's actually another trick we introduce here that will potentially be another way you can solve some of your problems. So to get started, we've got our spheres, our jitter, our transform, and we've got our animated set to 0. And this again is actually for the exact reason we just covered back here. We've got our sphere, our clip, our transform, our poly extrude, our assemble. I'm going to rename this to my bowl. And I have mentioned before, piece name is actually something different in Houdini, but piece is the default number or the default name for some of this, and it's also the default name that this solver will create for us if we forget our name attribute. So I like to do an intentional name. So bowl, maybe. That way, as I'm debugging bigger simulations, I can see exactly where the names attributes are coming from that might be causing issues. So now we've assembled this, so it is now packed geometry because I've selected create packed fragments. I now animate the packed fragment or packed geometry, which we have learned about in the past. In this case, we do not need to worry about a difference between the two. And we've got animated and active. Excuse me. In this case, actually, okay, good. I was thinking for practice, we should set active on this geometry stream for the exact same reason as before, but I forgot that this is already set for us as we were animating these spheres. We've got our objects here. Color, I'm going to be fine with ignoring because color is not used in our simulation, but for good practice, maybe I should. But I will not do that for now. And now for this one, same exact setup as last time. This is not working because it is not concave for our collision shape. If this was plugged into the collision geometry, we would now see it works. And the reason it is working is because the collision shape is set to concave. So when this is plugged in, and we have covered this again in the past, but I do want to re-emphasize it because understanding what's going on is very, very, very important. So right now, this is using the default collision shape of this object, and we are wanting to use it here. I'll leave this here. We wanted to use this on this left side of the geometry. And sometimes we might want to add this bowl to the simulation later. So that's one of the main reasons why we would use collision geometry in this first input. A quick fix to this one. In this case, since we do not want to simulate this bowl, is we can connect that to this input here, and we can set our collision geometry to concave. And the reason it's still working when it's static is because I've manually set my animated attribute myself, which again, we have covered in the past. And there we go. So now what I could do is if I did want to have these connected and I wanted to have this in the first input for reasons that might come up and actually will come up in many later projects, what I could do is this trick here. So this is the same setup. I've got my object, my points here being set to active as well as an animated attribute. I'm for now actually going to ignore, whoops, I do want it to extrude. And I'm going to connect this here. So I'm going to ignore these two nodes here. So now what I've got here is the same setup as this one over on this side. If I click play, and this is actually the Voronoi fracture previewing in the current cache of this simulation. So if I go back to the first frame and reset, we'll now see the collision shape of this geometry, which is going to be exactly what I expected. It is now going to be the shrink wrapped version here. So this is the same way I've set it up before. Assemble node here. I'm going to change this to my bowl. And this works correctly. And this is not going to be working. If I do want to have these here, a trick we can do is we can create multiple pieces of this geometry here. So we can essentially fracture, which we actually are fracturing. And if I do an exploded view, which we'll learn about more in the fractured or in the fracturing section of the RBD. But this exploded view just goes for each name and it pushes the parts away from their center of mass. But we can now see I've got multiple pieces in fact, 50 pieces of unique names because I have 50 points on my Voronoi fracture, or 50 incoming points telling this fracture node where to fracture. If I set this to 15 or any other number, maybe 55, it would now create those 55 unique name attributes. This now assemble node is set here. The important thing here is the Voronoi fracture, which we'll learn about more in the constraints and the fracturing sections. This is creating a name attribute for us by default, which is piece. So I now have the option to either uncheck this. Maybe I'll set this to fracture. So this now fracture, if I can spell correctly. This now is fracture here, creating a name attribute. I can assemble, which will go through here for each of these names. Transform, animate this, or set this to animated. And now, if I go to my solver and show collision shapes, we'll now see for each unique name attribute, we now have an individual piece of geometry, or an individual collision mesh generated. And if I simulate this here, we actually will see these objects collide with what is looking like the bowl, but is actually just this collection of smaller collision meshes. And it takes a little bit of time to compute this show collision shape. So unchecking that is going to get you a quicker simulation. But now again, on my points, on the output here, again, they're on points because this is all packed geometry. And we have learned in the past that actually we don't want to mix packed and unpacked. We'd rather it all be packed. But now my name attribute for my bowl is going to be named fracture. Oops. Fracture here. So if I had this, Voronoi fracture is creating the name attribute. The assemble is not recreating it. So I could enable this to recreate my name attribute, which would now have it here. Still the same one, still unique per piece. I can now reset my simulation, and this will work in the exact same way. So depending on how we want to connect these, if we do want to have them on this left side here, we could do some tricks to create objects that would be a little more easy to actually fracture, or excuse me, we could fracture them to make them a little bit more intuitive to come up with the collision shapes. But actually in the next example, we'll learn of an easier way to set this up. We can actually do it without fracturing. So that's going to be a nice and handy way to do it with a little bit less work. But this is going to be an important thing to learn. And we'll get more practice with this name attribute later, and we'll continue expanding because it is very, very important. So awesome. That's going to be the end of example 4, and we'll be back in just 1 second for example 5. All right, welcome back, and welcome to example 5 for our collision shapes section. So in this in this section, we're really just going to introduce this node here, which has tons of uses. But all we're going to be really doing in this example is just setting the collision shape. So this is the same exact example I had before, my animated spheres. This bowl that I've created, I've animated the object. In this case, this is actually not packed geometry because this RBD configure was creating this packed for me. So if I disconnected this one, what I might want to do is create my assemble node here to create my packed geometry and my name attribute. So that we have learned is the handy thing the assemble node does, but intrinsically this is also using a pack node But instead of us creating our name attribute ourselves, we can use the assemble node to help us with that. And if I go to the start of my time frame, my timeline, and simulate this, we can actually now see the collision shape is using this object here, which is the convex hull of my bowl. And if I play it, I won't actually be able to see inside, or excuse me, I won't actually have the collisions working inside the bowl. So the way we could fix that is with this trick here, but another way we can fix that is using this RBD configure node, which lets us set up lots of helpful properties. Whoops, I accidentally hit U to go up. I'm going to jump back in my section, and we've covered quite a lot so far, but we are all the way on this right side. I'm going to delete RBD configure. This one we'll learn about a lot in the next coming sections. I'm going to connect this to geometry. We'll see what it does. Is it does pack this for us because I've got create packed fragments here. And what I can do under collision shapes, this gives me a handy drop down to set a concave setting, or really any other setting here for my collision shape. I can now connect this here to my transform. And now this extra attribute will now help my bullet solver realize that we want to set this as a concave geometry. And actually this introduces the idea that we will do a lot in the future. So this attribute, all it does is this node, all it does is it sets attributes for us, and it gives us a really helpful way to find exactly what we need. But actually, if we did a attribute wrangle and we set bullet underscore geo rep, so s at bullet underscore geo rep equals concave, I believe that's what it said, concave. What I could do now is manually set concave. Connect this here. If I see this, okay, whoops, I should assemble this, so I should pack my geometry. I want to connect this to the first input. I now have my packed fragments here and bullet georep as concave, which is the same for this one. And this also gives us other helpful things to do. We can set the mass of objects, the bounce, lots of other settings here. This is really helpful because sometimes it's hard to remember what names you need for RBD. So these nodes are really helpful ways to quickly reference what's helpful. But now if I connect this here, concave, bullet, georep, and my hope is that this will now correctly show, there we go. Okay, awesome. It is now working correctly. And in this case, actually, we can see the error we have before, a mismatch of attributes for bullet georep. And that is only because this left side does not have that attribute set. And whether we use the RBD configure or set it manually ourselves, it'll give us the same result. But this RBD configure is also going to help us do a lot of different things later, and lets us also work in a way that can stay organized once we get really big setups. So I'm going to do a switch node to help indicate that this is either way works. And I want this actually connected to the first one, because this setup also is proxy geometry. So in a similar way that our RBD solver has geo constraints and proxies, our RBD configure has those as well. And I think that might be the end of this example. This here we did set with this RBD configure. But again, and I'll do it again because we really need to practice this all. RBD configure, or whoops, I want solver, so RBD Bullet solver. If I connect this here, and I had this in the fourth input for this one here, we'll now see that. And I actually believe I would not need to set this as concave, because I could do that in the, whoops, I could do that in the collision here. And if I preview collision shape, we can now see that is set correctly. So there's tons of different ways to set these up. Your choice of organization is really up to you. I'm going to delete that because we don't need it. But the more you practice and the more you make changes and modify some of these, the more it's all going to make sense, and you'll slowly start catching up, seeing what's going on and what's working, what's not. But definitely lots of stuff, and make sure you understand these fundamentals as we go, because they're going to be helpful once we start doing really cool stuff. So awesome. That's going to be the end of example 5. I do have 2 more prepared, and then we're going to do maybe a fun little bonus exercise at the end. But that's going to be all for this section, and I'll be back in just 1 second. All right, welcome back, and welcome to the next example for our collision shapes. In this one, we're going to do, again, a very similar example and cover some of the information that we already have covered, but we're going to do it in a slightly different use case. So with this one, excuse me, I've got my spheres. I've got a little bit of a point jitter and a transform moving them up. So again, we've seen this many times before. In this one, I've got my cube, a mountain node, a poly extrude to add some thickness, and then an assemble. And we've learned that the assemble node is handy because it can do the name attribute and pack the geo all in one helpful node. Then the next up, I've got my deforming attribute set here. And we have learned in the past that I can either set this deforming attribute here on my bullet solver. So if I connected this here and set this to deforming, this would work as well. And now I can see on my visualization, show collision shape, I've got my objects nicely interacting and animating with my wavy ground. But what I could also do is I could set this here on my, set this back to static, because I'm now intentionally setting this here to deforming, again on my packed fragments. And now this will work the exact, whoops, I accidentally hit this skip button, which is going to skip to the end and simulate everything. But if I go back, we can now see it works the exact same way. So this might be one way to do it, but another example, which actually looks like it is the exact same thing, is we could set this on the solver itself. So I'm going to go back to the start, reset this simulation, reset this one, and then select and reset this one here. And this is actually the example I just showed you, which we have covered, but now we can see that our deforming attribute is set correctly, and our collision shape, whoops, excuse me, our show collision shape for collision geometry, not this geometry, because this will be the spheres and this will be the collision. We can now see that this is updating as we might expect. So multiple ways to set that up, which are all very helpful to know. And then the way of setting this up here intentionally, we can actually use the RBD configure as well. So instead of doing all of this stuff for assembling and setting the deforming attribute, we could do RBD configure and just set this attribute to deforming. This will pack, create the name attribute, and set this deforming all in a single node. So if we go back, whoops, I accidentally connected this to the first input. I want it on the fourth input, and I want this transform on the first one here. But now, this will be the exact same. So again, this is nice and helpful to use. Sometimes I prefer to use these because in my opinion, these are easier to stay organized with. Because sometimes with this RBD configure, because there's so many settings, you might accidentally check one of these or have something set that you are not expecting. So always be aware of your geometry spreadsheet and always be intentional with your organization. It's awesome. That is going to be helpful, or excuse me, that's going to be all for this example. And again, this idea of setting here on this one would be very helpful if some objects were deforming and some were not, in which case maybe I will do a quick example because why not? So I'm going to create a box, rotate it, maybe place it here. I'll do another assemble node to create a new name attribute. This is set to $OS. So it will create the name attribute based on the operator string or the name of this node here. I'm actually going to set deforming on this object to 0. And I'm going to merge the two here. And now I will get my collision object from the cube, but it will not be deforming. And to better demonstrate that, maybe I could do a mountain on the cube. Maybe add some, whoops, that's too many divisions. Maybe add some divisions as well, and then animate this. So we can now see some kind of animated object. This is then being packed, set to a deforming value of 0. And now inside my solver, we'll actually see that the first frame of this object, which in this case is right here, is, oops, I'm going to go back. Right here is caching the current position of this mountain here, and it is using that to save a single collision geometry, and it is going to use that for the rest of the simulation. So we can have some that's deforming, some that's not deforming. This could even be animated if we did want that. But that is stuff we've already covered before. So I will not set that up. Maybe a challenge for you would be set that up if you would like. So awesome. That's going to be the end of example 6. I've got one more example coming in, and then we're going to have some fun and showcase a couple practical examples for how to set these up, but 100% from scratch. So from an empty network. So awesome. That's going to be all, and I'll be back in just 1 second. All right, welcome back, and welcome to example 7 for our collision shapes for our next section for RBD. So to get started on this one, I'm actually going to first select this solver and reset just so that blue bar disappears. This was what we covered in the last video. And here we go. We've got our active spheres again coming in from this side. Point jitter displacing some of these points. We've learned these are packed. The transform, moving it up. So the exact same setup we've done many times so far. And now, whoops, we've got our cube, or excuse me, we've got our grid here. And the other trick we can potentially do here is kind of an example extension from what we covered, I believe, in this section right here. So I'm going to do a C to color this really quickly. But this idea of fracturing geometry can be really helpful if we want to be intentional with our use of either animated or deforming. So I've got this on my left. This grid here, what I've got first set up is a scatter here, creating, in this case, 1,000 points. Relax iterations are turned on. I could even increase those. The reason I have this on is I want them to be nice and evenly spaced. This Voronoi fracture is now going to create a fracture of this grid. And the interesting thing about a Voronoi fracture on a grid is right now we're going to get back faces as well. So we want to create interior surfaces. We want to uncheck that. So it will leave this as a thin piece of geometry. And that's going to be a little bit quicker than if we first extruded this and then fractured it. I now extrude these 0.05 to give them some thickness. And I am now assembling, which is not, in this case, creating a name attribute, because this is fracture. This, again, we've covered in the past, the Voronoi fracture, which we'll get into more detail when we start our fracturing section. This is the name attribute is being created here. The assemble node, in this case, is recognizing or respecting this name attribute, and it's packing a new piece for each name or each unique name. But if I checked create name attribute, that would make it a new one here. So in this case, I'll leave it with what it was. For this specific example, this would not matter either way. But as we get more complex, we'll want to be very intentional with where our name attribute is created, because those will be important for our constraints, which the Voronoi fracture can also maybe help with, but I actually don't really do that. I like to set those up myself. So we've got the assemble. If I preview the exploded view, we can see all our individual pieces here. And all I've got on this right side is a displace, which is giving a little bit of an animated object, or excuse me, a little bit of an animation to my grid. So this is a very similar idea to what we could do here. It's a little bit of a cheat, and not necessarily a cheat, but a little bit of a different use case. But if I use a point deform, which is just a standard point deform, I've got my mesh plugged into the left, the rest points plugged into the middle, and the deformed points plugged into the right. What this will do is it will deform this incoming geometry based on the difference between the rest and the deformed points. So this is a very helpful point, it's a very helpful node to use. Similar ideas will be helpful in other areas of Houdini, but for now, what we are doing is we are animating this packed geometry. And now because this geometry is already packed, and then we are animating it after it's been packed, we can now use the animated attribute. I'm going to hit escape, go back to the start, and click play. Whoops, I have to set my display flag on my solver. And if I click play, we will see this works in a very similar way to if I had the deforming attribute set on the actual geometry itself. So if I had done a new solver here, I'm going to hit escape to cancel that and go back to frame 1. For this left one here, I do have this set to animated, but that could also be static because this attribute wrangle is setting that value here. What I could do is on this right side, connect this object, and instead of setting animated, I could do an attribute wrangle and say I at deforming equals 1. This will set my deforming attribute here. So I'm going to say set deforming, and on this collision here, if I leave this as static, because we've also learned in the past, we don't want to be setting animated and deforming to true or to 1. We only want one of them. All right, this is a good example, I believe, of mixing I might actually leave this in. So we'll find out exactly what's going on. So I've got my deforming here set to 1. Double checking I have it spelled correctly. My thought actually is I don't think there's a name attribute on this one. So I think that might be giving me an error. So it is being animated. It is set to deforming. But there shouldn't need to be a name attribute, I would assume, on the second input. Or on my collision. Interesting. Okay, let me figure out what's going on here. So if I manually set the deforming myself, it is not working. If I set it here on the solver, it is currently working. And I believe the reason for this is actually because this collision geometry is not packed. So if I do a pack node just to pack the geometry, which will create my packed geo, I don't need to transfer any attributes because none currently exist on this one that I need. I now set this to deforming, and I go here. There we go. So that is a interesting thing which we should be aware of. Apologies for not first catching that. It's been a long day of recording, and that is another thing to note. So again, always being intentional with your packing and whether your objects are packed and not packed, especially for this collision object as well, can be an interesting setup, or can actually result in some interesting setups. So I'm going to label this as, and this I'm actually going to set to static. So I've got my packed geometry. I'm setting it to deforming on the packed geometry. And on this collision geometry, I'm setting it to static. So this deforming is overriding the attribute set here. And now it's working as expected. So I'm going to do a little box here. I'll color these maybe a dark purple and a red. And I'll say for the collision objects, say note, for the collision objects, the order of packed, non-packed will have an influence on the attribute working as expected. So again, lots of the times the Houdini solver here is doing things for you. I am curious actually on a little bit more of why, but I'm not going to debug this. But for now, whoops, we've got this working here. So again, not packed, it is not working. Packed, it is working. So again, always be aware. This actually probably deserves a little bit more experimentation. But as we get into more projects, we're going to have a lot of fun practicing and getting this set up. So awesome. I think that might actually be the end of this example here. We've covered quite a bit of stuff actually. So I am going to end example 7 here, and we'll be back in just a second. I'm going to double check actually. I think this has all been covered. This is animated, this was packed. We animated it, or we pack it, then animate it, then set it to animated, and then this works correctly. The deforming was a little bit of an interesting use case because it had to be packed, but we should be good. I will add extra videos if we do need to cover additional topics on this specific one. But as we get into our future sections, we're definitely going to have a lot more practice. And it's going to be more helpful to see this in the context of real projects to get a better understanding of how to control and organize as these get bigger. So awesome. That's going to be all for example 7, and I'll be back with a recap of this introduction. All right, welcome back, and welcome to the recap of this current section of Level 6, Simulation Fundamentals, RBD Introduction. Everything you've seen so far has just been Section 1 of this level, or actually of the RBD section of this level. And we're going to recap a little bit here, and then maybe introduce what we're going to be covering in the next few sections. Well, actually, I'll introduce what we're going to be covering next first before we recap. So next up, we're going to have our constraints, learn a little bit about those, some more practical examples, which I might do a bonus section for those, maybe add in a couple ideas to this file here, but we'll see. And then fracturing, and then the actual applied setup of maybe creating some mini destruction scenes that will be a good use case to showcase what we've done so far. So back again to section 1 of what we've covered so far. We have had our introduction here to RBD. We've learned our bullet solver, and actually quite a good bit of information about the SOP level wrapper, which is this right here, for our bullet solver. So this solver itself, if I double click here, I actually get into a dive target, which is a different thing in Houdini. But if I go up here by 1, we can see this is the DOP network solver that Side Effects has nicely organized and set up for us. So without us having to actually use and set up all of this stuff ourselves, we can use a nice artist-friendly wrapper around this one here that lets us access the power of the solver, but without having to do all of this complex setup ourselves. We've learned that the bullet solver internally, so inside this SOP level solver, is using the RBD solver, and it works on packed geometry. So Houdini itself is doing a lot of the, well, actually Houdini and this tool itself. I just reset that to get rid of the blue line, but this is doing a lot of the work for us for organizing the name attribute, the active attributes, animated, and deforming attributes. So whether we intentionally pack our geometry, whether we intentionally create all these name attributes, that is up for us to either do, or leave this little tool here the option to try to do for us, which in some cases it might do it correctly, and we've learned about that in these past sections. But in other cases, it might cause issues. So we want to make sure that we are 100% aware of what's going on with our solvers so we can understand it, control it, and more importantly, debug it when things go wrong. So as again, always, if something doesn't work, slowly try to debug, make sure the attributes are set correctly, and then break down and isolate parts of the simulation to slowly find your error. So what we've covered so far, first was this little section on the name attribute. We learned how the name attribute is required, and Houdini will actually create it for us. The name attribute is actually used for our high-res geo, our proxy geo, our transform pieces, our simulation points, really for everything. And it is required, as well as packed geometry is required by the solver. But whether we set those or the tool or Houdini sets those for us is kind of up to us in how we choose to work. We've learned a little bit more about the difference between packed and non-packed. We actually introduced packed fragments and packed geometry, which for our use cases now, there is no difference we need to worry about between the two of those. The next one we did a little bit of example into the name attribute, how objects that share a name attribute are considered part of the same object in a simulation. So that can be helpful if we want to connect objects. We don't need to use constraints. We can just have them share the name attribute. But then the order of creating and saving the name attribute to our objects needs to be done intentionally, because Houdini will pack the geometry for us inside the solver. We want to make sure we are setting that in a way that works as expected. So typically our name attribute would be on the primitives. If the geometry is packed, then that name attribute might be on the packed points. But we want to be sure of where it is. This solver will actually handle some of the differences. So whether it's on points or primitives, once the geometry is packed, and I believe even once it's not packed, if we let the solver do it for us, it might catch many of our errors, but we should be aware of what we're doing just so we can help catch those errors ourselves. So we don't want to have them both on packed, we don't want to have the name attribute both on points and primitives. In the next section, we introduced the active attribute, which was very helpful for controlling either parts of the simulation that were to be set to be maybe animated only or added to the simulation later. So by combining maybe the active and the animated attribute, which we learned about in the next section, we can have parts of an object or objects entirely join the simulation at a later time, and even maybe start it being animated like a ship crashing, and then have that switch to active if we want to have it join the simulation. We learned how to animate these on our packed geometry, which had a nice sphere example, which was set up nice and in a nice and helpful way. We also learned how to do cubes to have some animated objects. In this case, they were not animated, but how to have active objects join the simulation at a later time. And then we introduced another workflow for having collision objects. So if we had the intention of maybe one of these cubes joining our simulation, we might want to have that on this first input for the geometry side of our bullet solver. But if we had no intention of these ever joining the simulation, it might be easier for us to organize these into the collision geometry for this 1, 2, 3rd, and 4th input here. So the way we choose to organize that is actually up to us, and then might be up to how we want to run the simulation. So what we want to have in the simulation at a certain time or other times. Next up, we learned the animated versus deforming attributes. So these were really helpful for actually creating and modifying some of our pieces here. We did learn that the point attribute, so animated and deforming, should be on points, that this is a attribute used by the solver to control the change either of the transform of a collision mesh or the transform and recooking of the shape of the mesh itself. So what that means is the animated object will only update the transform of the packed geo. So we pack it and then we animate it, and the position of that gets updated inside the solver. If we want to have the shape of the mesh actually update, we need to have that as deforming. So animated is more efficient than deforming because it cooks the single frame or the first frame for the collision. It gets the shape of that object, and then it transforms that at each frame instead of recooking the collision shape. Deforming will transform and recook the collision shape at each frame. So all very important. These are also important whether we set them on our packed geometry or if we set them on our unpacked geo. So being aware of where you set it up is important. The animated attribute has to be, well, the animation has to be done on packed geo if it's animated, and if it's deforming, we can do that at a different time. But for us, for animated, we want to have packed geo and then animate that packed geometry. We covered a few examples actually of I believe this was the collision shape for the objects, updating the collision shape, and then we learned that I forget which one this actually was. The object here, we can set deforming and animated, depending on whether we want to have the actual collision mesh update or just the position of that mesh. So that's very helpful and very powerful. We also learned that we do not want to have both animated and deforming set to true. So that actually did cause some issues in this section down here. But we learned that we want to have either animated or deforming. And we also learned in this one here actually, we learned that Houdini will set attributes for you. So in this case, we have a box. We set a attribute to 2 and 1 for attrib only on certain points, but default values are created for the other points. And when we merge a geometry stream, we've got sphere and merge, and for every single point, so for this sphere here, it has now created a default attrib value for attrib. So we have learned that it is very important setting these intentionally because Houdini will create those for us. So always be aware of what you're doing and make sure you're doing it intentionally, which is very important. Next up, we did some information on collision shapes. So this was quite a few examples on either convex shapes or concave. So if we want to have objects, we can set the collision geometry to concave if we are using this as the collision geometry here. So that's very important. If we want to have it be concave, we can also set, I believe it was down here, the collision shape to concave, either using a RBD configure or actually manually setting a string attribute. And the name of this string attribute we find exactly on the RBD configure node. So these nodes just set helpful attributes for us, but we could do these all ourselves if we chose to do so. So we learned a couple examples of how to make sure our collisions were working correctly, setting the collision shapes in a few different ways. We also learned setting active and animated attributes for these, and then doing a little trick here of creating or not modifying the collision shape, but we broke our bowl into multiple pieces. So although we were not using a concave collision here, because these are unique pieces, in this case 55 unique strings, we would have our individual pieces here all computed as individual collision meshes. So as we use different objects, we can control how we set these up and fracture these based on what we want to use them for. And then this was manually setting that collision shape with just this attribute. We had another example here for our wavy ground, which we actually used the deforming attribute, which in some cases might be quicker than if we did something such as this example here, where in this case we took a grid, fractured it, and then we displaced this grid with a point deform node and then fed this packed geo. So it was packed and then we animated it. We set that to animated and fed that into our collision geometry here. And then we also learned that this example here, if we have our deforming object or our object set as deforming for this collision input right here, if we set it on this solver here and set our collision type, currently it's on static. If we set it to deforming, it will work correctly. If we set that attribute ourselves outside on SOPs on unpacked geometry, we can see what happens. It will not work. So if we are setting that attribute ourselves, we found out here that we need to have our packed geometry first. And then we set our attribute, and then that works as expected. And now, because we've set that on our packed geometry here, we don't actually need our collision type set to deforming. That could be deforming, or we can set it to static, reset, play, and would work as expected because this is actually overriding our static. And we've learned that this kind of use case of setting these before, so intentionally setting these ourselves, can be helpful if we have some objects that are deforming, some that are static, and we want to control which is which. So awesome. That is going to be the end of section 1. Hopefully this all made sense. I definitely recommend downloading the files and playing with them yourself. Most of these actually are very simple to set up once you've watched through this project. And actually a good practice or a good exercise would actually be to recreate every single one of these yourself. So if you really do want to make sure you're knowing what's going on, I would recommend doing maybe not everyone, but as many as you possibly can to understand exactly what's going on, and then fixing common issues like this. So fixing those in smaller setups, like these little examples we have here, are going to give you the important practice you'll need in order to know what might be happening on your bigger setups. So awesome. That's going to be all for section 1. And then in the next couple sections, we're going to dive into some more detail and learn a lot more. So awesome. Thank you, and I'll see you in the next video. Welcome back. And if you made it this far in the video, then congratulations. I really do hope you learned a lot. A lot of work went into this one. A lot of information was covered. And I hope it was helpful to you, either getting your first introduction into RBD, or maybe refreshing and hopefully getting a little more of a complete understanding as to what's going on, kind of how it works, and some more important things you might need as you continue your Houdini journey. If you are interested in learning more, this is part 1 of 5 inside the RBD introduction for our Level Up Houdini curriculum. This is level 6, so simulation fundamentals. We're going to have lots of these for really just about every type of simulation you'd want to do in Houdini. And then the exciting level 7 is going to be some really cool boss battle projects for combining different types of simulations into full projects. So it's going to be a lot of fun. I definitely encourage you to check this out if you are interested in learning with a more structured curriculum. But if you are enjoying the free YouTube stuff, then subscribe. Definitely keep watching, and maybe drop me a comment down below if you made it this far, and let me know maybe what you learned most or what you found most helpful. So thank you again for watching thank you again for watching this far. I really do hope it helped, and I really do wish you luck learning. I will see you hopefully in the next YouTube video, but maybe in the Level Up program if you decide to join. But other than that, that's going to be all, and I'll see you in the next video.